Hi, this video is about taking you through the steps to compare different groups in Amos for a certain model. And let's first take a look at the model that we decided to work with, which is a model that based on the literature and with the bestest fit. Over here we are studying the content value credibility, which is conceptualized by two dimensions, the entertainment value and the information value. We are also studying the source influence for an influencer. So we are looking into the credibility of the content that they're providing, as well as their own credibility as influencers, source influence credibility. It is usually measured through four different dimensions: trustworthiness, expertise, similarity, and attractiveness. Then we're talking about also how this is one of the contributions is to look into the relationship of or the effect of brand fit. So in some research, one research that I looked into, they're looking into the interest in the product that affects your purchase intention. So for example, you are exposed or watching a video for an influencer talking about a certain product. If there is no interest, then you probably won't have a high purchase intention. However, we were not asking about a specific product. We just talked or asked questions generally about the general purchase intention through a certain influencer. Now, we would like to investigate the role of the brand fit on this relationship, on the purchase intention and the parasocial relationship. Also in another research, now researchers are highly using parasocial as the lead to purchase intention for social media influencers. So basically, content value that the influencer is responsible for, also the influencer pretty much responsible for these: trustworthiness, expertise, similarity, and attractiveness through source influence. But then we have two more concepts. The first one is the brand fit. How close is the influencer's credibility or content and source influence? How close is this to the brand image that they are featuring on their channels? So if there are a proximity in the image of the brand, of the product that they are featuring on their channel and their content throughout the time and their source influencer personality. Now, this is the brand fit, and I think this will bring into our study a lot of meaning to the practical contributions for businesses. Then we also going to study the parasocial relationship. The parasocial relationship is that you're going to get an influence over me through my interaction with you. When I build that rapport or that relationship with you as an influencer, then I follow you, and I will be influenced by your suggestions or recommendations. So for this purpose, we have also the parasocial relationship. Of course, you probably working with this kind of structure equation model. And with this is the same exact model, but over here we have a brand fit measured by 5 different elements or observed variables. Information value also measured by its underlying items, observed variables. And then here we have the content value as a second order construct, which is measured by these two first order constructs, and similarly to the source influence. Parasocial, on the other hand, is a first order, and we would like to see the effect of the content value on the parasocial and the source influence on the parasocial. We also would like to investigate, as one of the hypotheses, we would like to investigate the content value on the purchase intention and the source influence on the purchase intention. So ideally, we would like all these to be supported as hypotheses. Now, we don't have still literature to investigate the content value on source influence, if any, but we added this later on to get a better model fit and get some hypotheses to be significant. So we need to find literature here. And I have seen some studies talking about the content value and its effect on the trustworthiness, but a little bit distant. So we are still working on looking up literature where researchers have studied the content value, for example, on trustworthiness or expertise or any other measures of these, or directly into the source influence to support this move. Then we also have the following hypotheses: brand fit on purchase intention, brand fit on content value, brand fit on source influence, and also if we have a brand fit on content value and the brand fit on source influence, that would be probably sufficient. I'm not sure if we have any literature about the brand fit and parasocial. We have the literature about the brand fit and credibility, which is measured credibility by these two dimensions. All right, now we are running this model. Let me just look into the data. Yes, this is the data set that we have, and we're running the model. First of all, we have to look into the standardized estimates. All of them are supposed to be over 0.7, but in our research, we have manipulated or changed a little bit in the questions, so we didn't just take the questions from a study. So for this purpose, we're going to accept anything above 0.5 or 0.55 depending, and we have pretty much everything is above 0.5, almost 0.6 in fact, and 0.55 here. All right, so having this checked, now we need to check the relationships. Over here, it is very important that we also check the direction of the relationship. So for example, the expected direction of this relationship, content value, the higher the value, the higher the purchase intention, but over here we have it in the negative. So something is up, something is not adding up correctly here. So even if this is significant, there it's pretty much questionable. So I would say this might not be significant, and we're going to take a look into it in a bit. Also, as you can see here, brand fit is having a negative effect, but this may be due to the fact that we have this added line. So I'm going to get rid of this added line because we don't have the literature yet to support this added line. So let's see now if the relationship will still be in the negative, and I think it is. Yeah, so over here still it's in the negative. This means probably the sample size is not good enough and so forth, because or some of these relationships over here, the added relationships, are affecting this to be negative. Because if you've noticed, we had this is negative and this is negative, but when we removed that relationship over here, this has been rendered in the right expected direction, which is positive. However, it is so small, so I'm expecting this to be also insignificant because it's so trivial, so small. This is also so small, so I am thinking this is maybe most likely to be insignificant when it's really a small loading, as you can see here. And also when it's negative and I'm expecting it to be positive, this might also yield maybe it is insignificant. So let's take a look at our model. Of course, for the model fit, you need to have this below 3. You also would want this to the CFI, the TLI, and the IFI. You want all these to be ideally above 0.95, but 0.9 is still acceptable. If you have something in between 0.8 and 0.9, then this might be marginal fit, and not very acceptable fit, marginal fit. Anything below 0.8 is maybe suffering. So we might not even, this might not, if these are not acceptable or marginally acceptable, then this means that it is very difficult for you to accept or to validate these regression weights. So these regression weights mean nothing. Even if it's 0.81 and this is a high loading really, this would mean nothing if the fit of the model is not validated, of course. Then we go down to the RMC. The RMC, this is ideally supposed to be below 0.06. Not only the RMC, but also the high bound as well. And the P-close is supposed to be over 0.05. However, some researchers also accept the RMC and its high end or high bound to be over, to be below, 0.08. So we are gonna change certain relationships here if some of the these errors or some of the regression weights are not significant. So this might enhance the readings as well. So these are supposed to be below 0.08, ideally below 0.06. And of course, these values are very important for continuous data in particular, and they are supposed to be about 0.95. Ideally, of course, 0.9 is good, but in between 0.8 and 0.9 is marginal fit. Anything below 0.8 is suffering. Over here, we see that we have very almost approaching the 0.9 for the TLI and the CFI, so that's all right. Some researchers don't pay attention to the RMR, but if you have, I personally like to report the RMR. It is also supposed to be below 0.08, but some researchers look into the standard RMR, which is here under the plugins, standard RMR. You just open up this and then run the model again and take a look at the reading. If the reading is below 0.08 or 0.06 ideally, then you are on the right track. So here it is below 0.07 or 0.08. All right, there is one last reading that we look into when we are talking model fit. Speaking of model fit, also we talking about the goodness of fit, of course, but more and more researchers are staying away from the goodness of fit because it is very highly dependent on the sample size. So, but generally, if you have the goodness of fit and the adjusted goodness of fit, the higher the better. And 0.8 is considered really good and higher. Over here, we are approaching that 0.8, and we might get better model fit when we look into the estimates. Now, you can also get a better model fit if you look at the modification indices. So basically, the way that you do it is right-click and copy and go to the Excel. I'm going to talk a little bit more. It's going to be a little bit of a long video, but so over here, looking at the modification indices, what you need to do is, for example, I'm going to put here error 1, error 2. You want to see if there is any high MI value, modification indices value between two different errors. This might indicate a covariance among them. So let's take the MI here and rank it from largest to smallest. And what you want to take a look into is any errors that are so close, meaning any errors within the same construct. So if there is a high correlation between error 1, for example, and error 20, you are not going to covary these. You are just going to look into covarying errors within the same construct. So over here, for example, error 43 and error 44, maybe they are close enough to each other. But in fact, these errors here, 43, and this is 44 for two different constructs, no, we're not going to covary these. But looking at other errors here, problem over here is that I have 1, to 5 for model fit, then 31 here, 32, 33 for information, then 14, 15, 16, 17, 10, 11, 12, 13, 6, 7, 9, and then 25. So we have not really a very steady way of naming the errors, but it's okay. So I am around the 20s only. Anything in the 30s and 40s, I'm just not gonna look into that, because so error 13, error 34, not gonna look into that. Anything in within the same construct kind of errors. 12 and 4 sounds to be very far away from each other. So this is 12 here, somewhere here supposedly, here, and 4 is somewhere here, so I'm not gonna covary these together. So you need to just pay close attention. 11 and 10 are probably good candidates. Let's take a look at 11 and 10. So that would be over here. This is 14, no, nope. Here is 10 and here is 11. So in fact, I think we covaried these errors earlier. Wait a minute. I am going to save this as, and I'm going to put video. And I believe we covaried these based on the measurement model, but we shouldn't be using the same for the structure model. We need to investigate the modification indices again. So 10 and 11 here are showing good signs. So if you run the model fit, I want to take you through the whole journey. If you run the model fit now, I wonder if we're going to get better or worse. So here's the model fit. These are slightly probably worse here. So yeah, on the edge here, yeah, they're slightly worse. So let's see if we can improve this. 10 and 11. Let's take a closer look. So this is how you look into it. 31, 37, I'm not sure if we have any errors in the 30s here. Yep, we don't. If you want, you can run the model again to see the effect of this covariance between error 10 and 11 to check its effect on the model fit. But you can just randomly covary the errors. So over here, maybe a slight improvement. I'm not sure, I don't quite remember. It's the same almost. So it's the same because mostly the huge effect will be if the errors have the highest. So over here, for example, but these are not very much close to one another. 13, 39, 35, 16. 12 and 4 are far off, I think. Forty and 39 would be one of these constructs. No. 2 and 6. Let's investigate 2 and 6. So here's 2 and this is 31. Oh, okay. 6 is far off because this is 1, 2, 5 for the fit. So that's not the case. 5, 31. One and 6, let's check. We are up to 5 here, so no. 3 and 11, no. So you see how am I looking at these? 25, 28. Similarity is 25 and 28 is attractiveness, so we're not going to do that. And this is it. 25, 26, maybe. But I don't think that they're going to have a huge effect. Yeah, 25 and 26 in within similarity. So we're going to covary these. And we need to look into the questions and explain why they need to be covaried. Maybe the questions are slightly close to one another or has affecting each other. if this affects this, that affects this, and so forth. All right. Anything else? Maybe 11 and 9. Let's check that. So here is 9. Where is 11? 11 is here in expert, and there 9 is somewhere else. So we can just let be. That's it. I think these are not very, they're not going to make a huge difference, even if we find any covariance here. Let's look at the 7, 11. All right. 11 is somewhere over here, and the 7 is somewhere over here. So it's not gonna be all right. Covary this. All right, 10 and 15. I think they're far off. Okay. So based on the modification indices here, these are the only two that are supposed to be covarying, and this might not give us a better model fit, but maybe right now, because I am not paying closer attention, really, I maybe had missed some other relationships along the way. So looking into this, probably the same. All right, so this is why I saved it as a different model. Now I'm going to go back to the here to this model that we were working on, and I'm going to check the modification, the model fit again. But these, I haven't seen 1 and 2 covarying one another and so forth. So that is a problem here. We need to double check that. All right, so here is the model fit again. Yeah, here's the model fit is way much better because it has the 0.9 over here, 0.9, but I think I missed out on some relationships that my student has picked up better than me. So I think there were some covarying errors here that she was able to pick up, but I couldn't right now in the video very quickly. So this is just a demonstration, also a quick one for you to see how you can improve the model fit. Also, you can improve the model fit, for example, if you know that your sample is so small or you have a sample size issues, you take a look at these loadings, and if you can let go of any of these items, the lowest loaded, you need to keep at a minimum of 3 items for each construct. But for example, let's say here entertainment, you want to get rid of entertainment 1, for example, and see what happens if you get rid of that one, because it is the lowest 0.55. Take a look, a further look here. This is 0.9, this is good. All of these are 0.8 and above. Also, they are only 3, so I'm not gonna compromise. This is our only 3. So the only ones I'm gonna check is this, because it has 4. And the smallest here, all of them are very good loadings. But the expert here has 0.55. Let's see what happens if we get rid of expert 1. Let's keep an eye here on the model fit. The model fit here is 0.91, 0.89, and so forth. Let's take a look what's going to happen if we get rid of entertainment 1, for example. And you need to get rid of it along with the 16, okay. So entertainment 3. Okay, we need to get rid of it along with its error term, and don't forget to add the constraint here as 1. All right, and then run the model and see if this improves the model fit in case you have a very small sample size. This will also improve the model fit in certain context. So over here, slightly improving the model fit. We are not getting 0.9 here, so we're not going to sacrifice getting rid of one of them, but this has improved. It's 0.8. So it is your call. You can just say that you can see that this model fit is just a matter of collecting more data sometimes. So if you collect more data, you might get way much more better, or you can improve the model fit, and also you can get more significant relationships or hypotheses. As you can see here, when the model fit is better, you can also get better estimates. So let's just keep it as is right now and work with it as is. And let's take a look at the standardized regression error, regression weights. Over here, this is all significant because it is below 0.5. This one has improved a lot. Usually, this is along with other, let me take a look here. Oh, this is supposed to be significant really, but right now it is not significant. So this is a little bit concerning that we have the brand fit is not significant. Let's take a look. Yeah, it is 0.51. It's supposed to be below 0.5. So this is borderline brand fit on purchase intention. But other than that, all these are highly correlated. All right. What I wanted to show you how we can improve the model fit. Improving the model fit will probably render some relationships to be significant as well. It has to do with the ratio of the number of observations or data points that you collected to the number of items that you are measuring. All right, so over here we have entertainment 1 that we need to, I'm going to add it again. So it's going to be here. So this is entertainment 1. All right. And then I also going to name the error. Run the model again because it seems not to give us what we're looking for. Okay. Take a look. Okay. Do you see now? The fit has been affected, and if you take a look at the estimates here, in fact, the brand fit is you see, it is now 0.56. So if we get rid of entertainment 1 and probably get rid of one of these guys, probably, I'm just saying probably, we might be able to get this hypothesis to be significant. So the more data that you're collecting, you might get more and more hypotheses to be significant. So the lowest here is the 0.6. So maybe I need to this belongs to this, this belongs to this, this belongs to this, in fact. Okay, so parasocial 6. Let's get rid of parasocial 6 and see what's going to happen if we enhance the ratio of the number of records or observed data points or collected data points to the number of items, to the observed items, and see what happens. Hopefully we will get this model fit better. Yeah, now we got getting 9 here. We got rid of this too, okay, but it's not really that much of an improvement. So maybe we might need to keep the parasocial. Let's see if we have the, oh no, you see, the brand fit here is 0.57. It has even worsened. So this means that maybe I get rid of the entertainment here, but I'm just gonna keep, but even if I get rid of the entertainment, it's not rendering this relationship significant, the brand fit on the purchase intention, which is a very important hypothesis. So that is an issue here. We really wanted to investigate this relationship because or maybe we just need to so this is one of the things that you need to look into. Here, parasocial 6, we put it back. All right. And now we just stabilize the model. This is the model that we are going to work with. Even entertainment, probably I'm going to just keep it because I haven't got the brand fit to be significant really. That is unfortunate. So model fit is all right, is on its highest that we could get it. And now except this one, the brand fit on purchase intention. However, let me also take a look at, we have cleaned the data. We have cleaned the data in different ways. So I have different files with different data cleaned, which is cleaning the data with regards of the Mahalanobis distance. So it's one of the normality check assumptions. And here we got rid of the data points that has a very high Mahalanobis distance up to a point where you have it a little bit smooth, 87, 77, but there's a big jump here, so maybe we might need to clean these points. However, cleaning the data also could affect the model fit along with the significance. Over here it was 0.894, it has become 95, a slight improvement. So also work on the data cleaning in the multivariate outliers, and this might affect the significance of the hypotheses and the relationship. So we were looking at the brand fit and on to the purchase intention, and as you can see here, it is significant. So using this data point in particular, using this data set in particular, the one that I've cleaned, because my student cleaned the data set, I cleaned another data set. So you can see also this as a factor that affects the significance of or rendering certain hypotheses significant. So as a student, you really need to not clean your data in one step. And this is one of the things that I described in one of my videos. You need to take this, click, right-click, and copy. Let me give you an idea on how to do things right. And I explained this in one of my videos. And I said the way to do it, the way to go is, of course, you are going to, it is already actually ordered highest to lowest. And you are going to see what happens step by step. So for example, you call this data set as data, for example, SEM. Then you call it data SEM minus 1, meaning I'm going to take off only this point and see what happens. Meaning how the this value also will improve, which is the value over here under the assessment of normality, which is the value of the critical value here. Ideally, you want this value of the critical value to be 5 or below, so that your multivariate assumption will be met, and thus you could have the assumption satisfied for using the maximum likelihood. And then if you get rid of one more, then you have -2, -3. So I keep all these data files available. One with only 1 omitted, one with only 2, one with only 3, and so on. I be very careful so that when I get to the point where I'm looking at the model fit and all that, I might have to use different data sets to render the model fit. But of course, with this case of research, I think it's a waste not to collect more data. I'm going to collect more data probably later on, not necessarily on European millennials, but any millennials, using the guidelines of European millennials characteristics and see if they also apply on other nationalities. That would be interesting as well. And then we take the whole data set, maybe a data set of 400 data points or so that we can render more hypotheses, hopefully significant, and at the same time enhance the model fit. So the model fit, as you can see, is very much correlated and dependent on so many issues. First issue is the multivariate assumption. So you need to get rid of certain outliers based on the Mahalanobis distance, and this may affect, as you can see, the model fit. This is number one. Number two is the of course, the number one very big one is the ratio between the number of items and the data collected. So the ratio is 1 to 10. That is a standard. So if you have how many observed over here, you have 5 and 4 and 5 and 3 is 8, and 3 is 11, and 4 is 15, and 3 is 18, and 3 is 21, with 3 is 24, with 4 is 28, with 3 it is 31. So you need minimum valid 310. I would suggest collecting 330 so that in case you have any outliers or any other issues, you can get rid of it with ease, or 350 rather. So based on your model and how, if you adding more, like for example, if you here measuring credibility with more questions, you will need even more items measured. In any case, guys, I hope this demonstration has helped you improve the model fit. And model fit can be fixed with more data points, ratio 1 to 10, data points collected versus the number of items observed. Second is cleaning the data through the Mahalanobis distance to improve the getting rid of the multivariate outliers. The last one is also getting rid of the very low loading. So for example, if you have 0.5 as a loading or 0.4, anyway, anything below 0.5 you need to get rid of. Ideally, everything is supposed to be over 0.7. We attain this in most of the measures. This is 0.67, almost there. And we have changed some of the questions. If you change the questions and you don't take it from another research, then you can accept anything 0.5 and above. In our case, we are lucky. Everything is above, almost above 0.55 or 0.6 rather now. So we are just in good standing when it comes to the loadings. Another thing, as I told you, you might need to get rid of some of these items if your data set is so small, but better than doing that is to collect more data. Now there's another factor, which is the multicollinearity factor. So in fact, we found out in here, let me take a look at the video here. So this is the same thing but with more relationships, and we found out that let's get the good data set here. We found out that trustworthiness has a multicollinearity of 5 and above. So usually some researchers might say, oh, below 10 is okay, others say below 5 is okay. But in our case, for example, if we get rid of this, even though we couldn't, because this is part of the theoretical framework, we can't really. But I just wanted to show you that also multicollinearity maybe can affect the model fit. But also be aware that we cannot compare this because we are having more relationships here. So let's put it back as the previous model. The previous model, we had this, we didn't have this, and we didn't have this, right? So now it is a fair comparison. And we only have 1, 2, 3, 4, 5. Yeah. Okay, so now let's take a look at the model fit, showing you certain factors that could affect the model fit. As you can see here, this is actually not improving the model fit, as you can see here. But I wonder if it's, let me check if it's the same relationships and the same structure. Oh, sorry, I needed to save, I meant to save it, but it's running. Okay, so this is the video, this is, so 2 here, 1, 2, 3, okay, 2 here, 1, 2, 3. Yeah, it's the same, but it wasn't improved. So I think maybe just removing the highest multicollinearity item, not the whole construct, might make a difference. Well, since we have only 3 left, because we probably got rid of only 1, and this is what I was probably trying to say. We have 1, 2, and 3. We got rid of 3 because of multicollinearity, and then we got also a better model fit. So we have the Mahalanobis distance, which is the multivariate outliers, affects the model fit. Of course, before everything is the number of data collected as a ratio to the number of items measured in the model. Then we have multicollinearity, and you need to get rid of any multicollinearity. This thing is anything above 5. Ideally anything above 3, but if you can't afford getting rid of so many questions because you need a minimum of 3, then you could probably go with above 5. That would be all right, but anything above 5 I doubt, and it's going to have a low effect on the model fit unless you collected a lot of data, so that's all right probably. But this means that you have redundant questions within the same construct, maybe. So you need to say, I reviewed the questions and I see that there is no redundancy. So that is also something that you need to point out. And then, as you have seen earlier, the modification indices also could affect the model fit, and the weights here on the regression model could also affect the model fit. So there are so many things that you could try to manipulate and work with so that you can improve the model fit. The best out of everything is collecting more data, then looking at the loadings, then multicollinearity. Then there is also what we call it the corrected inner correlations. And the corrected inner correlations, I think you can get it from your data. You can get it from a scale, reliability. I need to get the data here. So you get it from scale, reliability, and I think you need to check on the options, the 2 options that has to do with scale. So you can also take a look into that and check if this can improve the model fit. So I hope this video has helped. It's about improving the model fit of your structural equation model, and I will see you in the next video where we're going to talk about, or continue talking about, how to compare different groups